Good morning, people. Here is a video on some exercises that relate to my previous lecture on filtering and scratch the surface of reverb. Good. So the first thing we're gonna look at is verifying all the impulse responses for infinite impulse response, IIR, finite impulse response, FIR filter topologies, and we're gonna try to make low pass, high pass, and COM filters out of both of those, so 6 things in total. Great. So first thing is a list. Let's start with the impulse itself. Kind of know what the expected impulse response is, so I'm able to verify it like that. So first thing is a generator, a function that will return the filter itself. And the reason why we build a function within a function, something like this, is that we have a scope for storing variables that will be available for each run of this function. But then again, these are variables which are scoped, so they're local to this generator and they don't extend beyond. Therefore, you could create many such filters and not run into problem with sharing variables. So the variable we needed here, if you remember in the lecture, was the storage for the previous sample value. But actually what I'm going to do this time around, I'm going to also have an argument for the coefficient, defaulted at 0.9. So this means that when I run my generator, I can specify the coefficient value for the filter, 8. And then what I receive is my filter, which will run with this coefficient and store the previous values. Okay, so the filter itself has the input value. And then, what shall we do? Let's do an infinite impulse response. Then it's going to do the math, which is add. So the previous is previous plus in, and I return exactly that. Okay, so what I'm saying is my previous value starting at 0. So as the first sample comes in, I will add 0 to it and call that the previous value, right? So I'm storing away into the previous value, I'm storing away the output value, right? And therefore I'm creating a feedback loop. Okay, that looks good to me. Function filter, and then our final signal is a.collect, and then we're gonna pass the function f, the filter, to that, and this is what I get, which is funny, although obvious, because what happens here is that each time the next value is 0, the previous value has already been 1. So I get a series of 1s, because one thing I didn't do here is I didn't multiply by the coefficient. And if I do that, then what I'm gonna get is this. Okay, so I get a neatly decaying sound. Now this is not necessarily correct, because you see I start with 0.8. And I should be starting with 0.9, I believe. So actually, what I would have to make sure is that I'm not storing away. Let's see what I'm doing here. So I'm adding the previous to the input and times coefficient. Actually should work. I would think it would. What's going on here? Coefficient. I mean, the brackets don't do a thing, obviously, because it's a row of things. So typically this is a kind of a hacked filter because it uses the coefficient only once. Let's do the real thing, which is input times coefficient and previous times 1 minus coefficient. Okay, so if you're interested why this is the actual IIR structure. Oh yeah, that's why 0.8. Sorry, so it wasn't wrong because I actually changed the coefficient here. I was kind of looking at 0.9. Good, so let's do the 0.9. And now it's actually going to be a better filter, I would hope, because I'm actually preserving the energy. Okay, so that's the low pass filter. And actually, well, let's keep the simple one. To hell with preserving the energy. Now, because this is fairly straightforward, because we know what we expect from the impulse response. What is going on here? So this is A, this is G, this is that, and this is my impulse response. Great. And then let's look at that. So the impulse response of an infinite impulse response low pass filter is actually an exponential decay. Okay, so the thing about this is that to understand is that what it actually means to process a complex signal with this, what you're actually doing is you are applying, you're kind of inserting this decay for each incoming sample. So if you imagine a sample of this height coming in, obviously, like it is now, then you produce such a curve and stick it out. Now, if the very next sample, which is currently 0, but it wouldn't be 0, you imagine it here, and it would be slightly lower, for example, then you would insert the exact same decay curve starting from this point and add it to this one. And then the third sample, for example, is really high. What that would do is would again insert the whole curve starting from that point, so you would actually get a kind of a whoop jump there. Okay, so that's what FIR essentially does, an infinite impulse response like this. Okay, so let's just look at the low pass filter, the high pass filter. So if you remember from the lecture, the main difference here is that I have a negative coefficient. So actually I don't even have to do that. What I can do is make it negative here. And this is the set of values that I get. And it looks like this. Okay, so what that does is it really accentuates the high frequencies. And most of all the Nyquist frequency, because this is the Nyquist frequency here. It is alternating samples at half the sample rate, right? So I have an impulse. I mean, I'm kind of losing the original impulse with this, which was 1. Then immediately I drop down, go back up, drop down, go back up, drop down. And the same holds what I've just explained. The fact is that that you are essentially adding up this response after each incoming sample to the rest of these. That's essentially what's going on. Okay, so that's the high pass filter impulse response, and then the comp filter has everything to do with longer delay times. Okay, so I don't want to mess up the previous one before we create a finite impulse response. So let's do the delay line. Well, in the delay line here, my previous values has to be an array of things. Okay, so I will fill an array. Let's do 10 samples of 0. Okay, And then in order to make this circular buffer, which I didn't talk about and I didn't really plan on talking about in this course, it's kind of a low-level implementation, but the thing is probably not very difficult to explain, is that if you have an array of 10 elements, right, and each time you run the filter, what you need to do is you have to take out the last element and put in the next one. What you get is a need to, I mean, initially you would think you would have to shift all the values, but shifting all the values is really inefficient, especially if you have more. So typically what you do is you have all the values stay in place, but what you shift around is the pointer. Okay, so actually I'm thinking let's make a separate circular buffer generator, just so we can test it and then we can use it in here. Okay, well, hell, it will take a while, but never mind. I hope you're having fun. Should be able to last. Okay, so this will be my circgen. So it's a function and it returns a circular buffer, which is a good exercise anyway, generating functions. Good old functional programming. There are a few functional programming languages like Lisp. You'd be surprised how many things you can solve by generating functions. So the parameter here would be the length. Let's start with 4, just so we can test it. And then what we do is we have a variable, which is this thing here, the array of zeros, and we have a pointer. Okay, and then we return a function which will always take a sample in, and it will output another sample. Cool. And then what happens there is the following. The pointer starts at 0. And what I do then is I will take the array, sorry, this is my memory list. Okay, so what I need to do is I say into the memory 0 I will put the input value, and into memory 0 minus 1, sorry, 0 I should say pointer, and here pointer minus 1, I should output that. Now the issue here is that pointer minus 1. Okay, so how do we deal with that? Well, I think this basically the most straightforward thing to do is a modulo operation, which is this, because it returns the remainder of a division. So if I take modulo 4, 0 modulo 4 is 0, 1 modulo 4 is 1, 2 is 2, 3 is 3, 4 is 0. So it's a kind of a circular function. It will actually yield a sawtooth wave. So if I go on like this, it goes up again, and then at 8 it will drop back again. Okay, and the nice thing is that minus 1 is 3. Okay, so what I can do is I can modulo both pointers like that. So they're wrapped around and they always talk to available things. And sorry, this needs to be length, which won't work here, so I will have to make that right here. Okay. This is my memory cells. Okay, length with zeros. And then input pointer. Okay. And that's actually the last line, so that should be output. Does this look good? I hope so. Let's see what this does. So we get a function, and then we're gonna do a circular buffer, which will be a circgen dot value. Use the basic one. Okay, so that's a function. So let's see if this works. So we first let's send it a 1, a 2, okay, and it returned a 0. And then I'm gonna send it to 3, and it returns 0, 4, 5, 6. Okay, so it doesn't seem to work. 7, it doesn't work at all. Okay, so let's see what's going on. Mem pointer. Oh yeah, well, one thing I forgot is to increment the pointer. Okay, so pointer is pointer plus 1. And another thing which I'm doing here is that I'm actually reading the previous sample. So I actually expect this to work as a 1 sample delay rather than 4, but that will be a quick fix. Let's start with 7. Okay, 1 was there already. 1 shouldn't be there. 7, 6, 2, 5. Okay, that's because I'm outputting the pointer value. Great. That's why I need to output the output value. This is all very educative, all the mistakes I make. I hope you realize that. So start with 5, 0, 4, and there's the 5. Okay, so I have a single delay, single sample delay. So what I have to do is I have to subtract 3 from the pointer. Okay, so that will be the 3 previous values, and then let's start with 7, 6. There was this, 7? Oh, horrible. Did that just not work? 3, let's double check that did work. This did work. Start with 6. Okay, 0, and then 5. Okay, now it's good. Another 0, 4, another 0, 3, and there's the 6. Okay, so actually I've delayed it by 1, 2, 3, 4 values. Okay, so that's now working for 4 input, 4 values. And instead what I have to make it work for any length. So I'm taking the modulo of length here and the modulo of length here, and I'm subtracting here len minus 1. Okay, because obviously if I subtract the length I will run the whole circle and get the exact same value that I've just put in. So this looks good, and now we can test it for any old length. Let's do length 3. Start with 6 again, just so we can compare. So 6, 5, 4, and there it is already. Okay, so that was the 3rd, here it was the 4th. I mean, I can go on just to verify it does work like that. Okay, well, hopefully that wasn't too painful, but definitely informative, I would say, because this is the lecture on circular buffers. Typically I kind of excluded it from this course because it's all ready to go in SuperCollider, but could be useful. It's a useful technique. Great, so now that I have a circular buffer I can actually use that here. So I'm gonna have my circle here, and then what I'm saying is circular buffer is circgen and 6. So right now what I can do then is I say that the previous value is actually the delayed value of the in times the coefficient. Okay, so if I do circ dot value. So I delay that by this amount. That will be my previous value, okay? And my output value, let's make this slightly more clear then. So obviously I have circ, I have previous, and I have the output. So that is my previous value. Well, actually we're building, what are we building? We're still building an infinite impulse response. So in that case, this is actually my output value. Am I saying the right thing here? I just delay that and I plus the previous value there. Okay, fingers crossed. I think I'm slowly gonna be confusing myself, which is so educative. So that's my generator, this is my function. Let's do a +9. And I'm not sure if I have enough zeros there, but this is definitely not the response I'm looking for. Okay, so what I'm doing is, as I figured, I'm gonna be confusing everyone here. And I'm a kind of an escapist. I would be inclined to say, well, bloody hell, forget it. But let me spend a bit more time with this. So what's going on here? So we kind of tested the circular buffer, the delay line, I should be calling it. So that shouldn't be a problem. Maybe we can simplify this for debugging. So let's just say that we're gonna be outputting the delayed coefficient, the delayed inputs times coefficient. Let's try that. Here we go, and that does look good. Okay, because I've delayed by this much and then nothing else happens. So what I need instead of this is that it recurs again at a lower sample value. So what I need to do is I need to store this into the previous value, and the prev plus comes in here. Okay, fingers crossed. Ooh. Previous plus not understood. Okay, I didn't initialize this to 0. That's an issue. And I'm thinking, actually I want to multiply the input value only. Here we go. Fingers crossed. Hardly. I would expect it to recur back here. So we are previous value. This is what we output. Should I leave it at that? I'm kind of proving that I'm not a great filter designer, which is obviously the case. Kind of spoiled by the availability of great ones. More of a user. Is this definitely not working? It definitely isn't. Let's just think of it again. Well, trial and error while we're thinking, but I don't think that would necessarily change it. Nope. So previous is the delayed of the, I thought the other, so what we do is, maybe I should look at the FIR structure. Although, as I said, I'm not doing the real FIR structure because I'm using the coefficient only once. But let's actually delay the input value and multiply that with the coefficient like that, and to that we add the previous value. This actually starts to make sense to me right now. Although I think I've lost the educative potential of this. But I'm still not getting my little IIR response here, to be honest. So something is going somewhere. So obviously I'm not, if I would now multiply the whole thing. And the other worrying thing is that I start getting everything after that. So I think I shot myself in the foot by setting an exercise like this. Okay, so now I've delayed the whole impulse response. But actually what I would expect is these to be spaced with that duration as well. Let's do a shorter one just for laughs. But it doesn't really do the thing I expect it to do. So what am I doing? I'm saying the previous value is the delayed input value plus the previous value times the coefficient. So maybe if I let's look for let's look for a bloody IIR filter structure. Come on. I hope you're bearing with me. So here it is. Is there a simple one? Let's put in great design of IIR filters. Someone knows the trade, obviously. Oh, except it's just the first thing. Let's just put in a first order, and then hopefully here it is. Although this is more than that, this one. Okay, so this would be the full one. So you multiply the input with A and you sum it with a delayed version times 1 minus A. So I'm not quite sure, as you see. What am I messing up here? So let's see. Obviously I'll do just the A, or no, I should do just this one. So I'm summing the previous delayed yep, so I need to delay the previous value, and that is in time coefficient. Does that do it? I'm very hopeful at this stage. Here we go. Yay, that does it. Okay, so this is the impulse response of an IIR comp filter. Okay, so every impulse that comes in will be repeated with a certain time delay, this amount. Okay, so the educative aspect of this adventure was look at the bloody plot and don't act all too clever. Great. Cool, so now we come to the FIR. So first of all, this basic one. So obviously I'm uploading these things, so I'm gonna preserve this as the IIR, LPF and HPF. This will be my circular buffer, and this will be my IIR comp filter. And then I will do a FIR, LPF and HPF right there. Cool, so I have an impulse, And now the difference is that we are not storing away the output value, but we are just storing away the input value. Okay, but we are doing this only after we have output something. Okay, so in this case I will use an output variable as well. So what I'm going to say is my output is previous plus in times coefficient, and then I store away the previous value. Sorry, I store away the input value as the previous value, and then I output the value. So this should be my generator, and then my filter is F, and then I can collect F. Collect F. Did this work? Function, what did I mess up here? Plus, okay, the previous, oh sorry, that needs to be out equals. Okay, that's a mistake. Here we go again, and there it is. So what you get with the FIR is just 2 sample values instead of getting the whole exponential decay. Okay, so the same thing holds that I've explained, in the sense that you are kind of repeating these 2 values for every incoming sample. So you understand how that is smoothing out the signal. That's what I've been going on about in the lecture. So if you have a really sharp peak, which is only a single sample, what you will get is 2 sample peak. So you're broadening all the peaks. So that's what's going on. And actually, if you take an impulse response of a room, right, so you record its response, or for that matter of an electrical device, you record what comes out of it in response to a single impulse, which is typically a series of different sample values. Then what actual convolution does, direct convolution, it uses a really long FIR, just like this. So for every incoming sample, it will reproduce the whole impulse response at that level, and then stack those up one after the other, add them together, and that is your direct convolution. So your convolution reverb actually does FIR deep inside, although implementations, they use an FFT based, a spectral equivalent of that, because this is really costly. I mean, now I have a single coefficient, which is a first order FIR, and it's fairly efficient. But if I had a direct convolution, then I would need the amount of coefficients that corresponds to the amount of samples in the convolution kernel, which means that, I don't know, if you have a 2-second kernel or a decent room, then that's 88,000 coefficients. So you see this, that can really cause a problem in efficiency. Okay, so that was my finite impulse response low pass filter, and then the high pass filter version will be the same thing with the negative value. And then, well, due to the way I've coded it, I don't see the first input value, which was 1. So it's actually the input value, and then immediately it goes negative, and then to 0 back again. So for a low pass filter, we had doubling of we have another one of the input values, and for this one we get the exact negative of the input value. And in that sense, you see, if you have a fairly wide peak, it will make it narrower, because it will immediately kind of counteract it. Great. And then finally I would go and make an FIR comp filter. So similarly to this one, what we do then is we say that the output value is the delayed previous value plus in times coefficient, and then the previous value is the input value. So we store the input value, not the output value, and then we output the output value. So that should do that. Here is a 0.9, and that's what it does. So instead of a series of repetitions from an FIR comp, you get just one repetition because it doesn't recirculate. There is no feedback. And then with a negative coefficient, you get a funny thing, I would think. Negative coefficient. That didn't work because of that. Oh, and sorry, here is my coefficient. I didn't necessarily need to do that. And here it is, so it was a positive one and then a negative one. I could be sorting out the first value, but just taking a lot of time now, so I won't go into that. So here when you see the IIR comp filter, oh, that's the exact one that I was about to say something over. So if we have IIR comp filter, what you actually see is a kind of a feedback delay line. Okay, so this will come back when we do the Schroeder reverb, because if you do comp filters in parallel, it is actually the same as a multi-tap delay line. Great. That took a while. Nevertheless, hope you like that. Cool. Number 2, let's create a list processing rise decay filter. The reason I've put this here is because I forgot to talk about it in the lecture. Sorry. And the thing about rise decay filters is that you use them more often than you realize. Typically, compressors need this type of filter. And what they do is they have a different coefficient for rising and the falling portion. And my escapist self suggests to leave it all together. But hell, let's fight it. So what I'm gonna do here is I'm gonna take an existing implementation of my FIR, because actually all you need to do is you need to apply a different filter, although yeah, it won't work. I mean, I'm not even sure. I've actually looked online for a sketch, but couldn't find it. This is kind of purely my memory. I think in the DAFX book from Udo, there is one of these, and that's in my office, and that's locked away now. No use there. So, shall we try to hack it? Well, I've just learned from the previous example that my memory is not necessarily great. So I'll just give you a kind of outline, and then you can try to code it yourself. So typically I would have 2 coefficients, and one would correspond to a rise time and the other one will respond to a decay time. And then what I would do is I would do something like if, and I could, shall we see if I can get it done? I'm so undecided, sorry people. So typically what I would do is I would say that if the input is larger than the previous value, then my coefficient to be used is coefficient 1, and otherwise it is coefficient 2. Right, so if I am larger than the previous value, which means I'm rising at the input signal, then I have this value, which I will make rather small, and then if I'm falling, I will have a rather high value. And then the whole filter runs just the same after that. I believe that is actually it. So this is an FIR. Okay, so I don't expect to see too much going on, but potentially. Okay, soft one. What's the issue with that? Oh, I didn't close that bracket right there. Okay. Good. So let's see if I can test this. So my testing array. So let's do a slow rise first. Let's say 0.2, 0.4, 0.6, 0.8, 1, and then a few zeros. Okay, so that's my slow rise and fast decay. And let's do something inverse. So let's do fast attack, and then slow decay, 0.8, 0.6, 0.4, 0.2, and then zeros back at the end. Okay, so this is my input signal test. And then what I'm gonna do is I'm gonna get, I think I did evaluate this one. So I'm gonna do fg.value, so I get a function out of that, and I'm going to do a.collect f is my function, and I'm gonna plot that against the thing. Okay, so this is what I had. So I had something which is supposed to have a slow attack and a fast decay. No, fast attack and a slow decay. So what it did is when I had a really sharp jump, it actually overshot the jump, which is a bit funny. And here it did something to the attack portion. It kind of made it lower, which is a bit funny. So it did something different for attack and decays. And that's what I was after. Obviously I don't have the sketch here, I can't check it, so I'll leave it at that. That's the theory, worth knowing. Rise decay filters exist. If you really want to develop these things, obviously you're laughing at my incompetence. Great. Next one, 3D, using sample delay code, single delay, one sample delay, code FIR and verify the spectral response in relation to the coefficient. Okay, so on the server, we can also create filters, especially the feed-forward ones, because there's an issue with feedback. I was kind of planning on doing that. I will be running out of time. So the single sample delay is sample one dot delay one.ar. Okay, so what we could do is we could make a signal which is white noise, and then we could verify the spectrum of that. go one by one. There it is, fairly flat. And then what I can do is I can take a delayed version of that. So delay1.ar of A, and see what happens if I add the two things together. So this would be my FIR low pass filter. Okay. So you see it removed the high frequencies, but only very slightly at the top. I hardly heard it, especially because I'm running 96K. And then if I subtract the two, I get a high pass filter, just like that. Okay, so that went quickly. Then the comp filter, what it would do is it would need a delay which is slightly longer. Delay 2, is that just 2 samples? Yes. So I'll just use the delay, non-interpolating delay. Okay. As a reminder, I think it works with seconds. Okay. So whatever, I'll take first thing is the input, then the max delay time, and then this should be 10 milliseconds. Let's sorry, this is 1 millisecond, which should be fine. That's then about 96 samples. We should hear a lovely little comp filter, okay, with all the notches. And then if I have an even shorter delay time, then I should have fewer notches, just like that. Okay, there you go. So those are those, and then shall we do that? Let's do everything. I can show you that you can actually create an IIR as well, which is slightly troublesome, but never mind that. What I'll have to do is I will have to rerun the server with block size 1. Okay, so what happens in SuperCollider is that every UGen runs a whole buffer of samples, which is the size block size, and typically 64, I believe. So what happens is that first the white noise code generates 64 samples, and then the delay processes those 64. They go out and then back again. So that's the reason why I can't make a one sample feedback between UGens, because it would be at least the length of the block size. But I can reduce the block size to 1. Now if I do this, most of my processing will be largely inefficient. Although, who knows, maybe you have a really fast machine these days and you don't run too much code, so you can afford block size 1. I understand that with the Bella little embedded audio processor, the hardware can run at these block sizes as well as at these buffer sizes, so you get extremely low latency, so that's rather cool. But typically a standard sound card will not run below 64, maybe 32, but typically 128 I think is the minimum you can get away with. And that has to do with the latency of the processing. So maybe if you're watching this in 5 years from now, this is just historical of historical relevance only because everything runs block size 1. I hope to live to see that. Okay, so that's the bit about the buffer sizes. So the point is that regardless of the sound card buffer size, I can run the code, the processing, with a smaller size. Okay, so I have that. and then I can boot my server with this block size, and then I can try to create a single sample delay. So let's do that first manually. So I'll take a trigger AR which is really short. So let's do 1/10 of a microsecond. That should be about 1 sample, and on 96K, and then plot that, and there is my single sample. Okay, so what I can now figure out is whether I get single sample feedback through this, and the feedback in SuperCollider works by sending it to local local out. So I'm sending out the A, and then I can have a local in, which is the return from the feedback, which is just that. So what I'm saying then is that I'm outputting the return of that feedback plus A. Okay, so what I should get here then is 2 samples, which is something I don't hear. So this is my feed. This is my no feedback. So what I really need to do is I actually have to send out that A, which already contains the local in, to create the feedback, and then I'm listening to A. That doesn't look too good. Local in, so trigger. Oh yeah, this has to be is A plus local in. Okay, and now I have a line of those values. So what I can do then is get a little decay in there. So what I would do is A is A plus local in times 0.8. And there's my decay. Let's take a slightly higher coefficient to see a lovely little decay. There it is. So actually I can make an infinite impulse response filter. I mean, this is just not very useful, I would say. And then just to verify that this did make the difference that I'm talking about, if I take a 64, which is the standard thing. Okay, this didn't quite get there. This is what I get. Okay, so we still have a feedback topology, but now the delay time is that much longer. So this is now a comp filter, and a second ago it was just a first order filter, whatever it was, a low pass filter. And I can look at the scope of that as well. Okay, well that didn't satisfy me hugely, so let's do it with white noise, a continuous signal. There we go. So you kind of hear the difference to the other comp filter, because this is a peaking one. Okay, so an IIR comp is a peaking one, and which was this, and so the FIR, this one is a notching comp filter, this is a peaking comp filter. So just for future reference, this is FIR comp, and this is IIR comp with the potential of shorter sample delays. Okay, I hope you can still bear with me. I'm kind of running out of force here. So let's look at the spring and ball eugens. So these are also filters. That's the interesting thing. And then we can figure out what kind of spectral response do they have. That was the idea here. So I will have a white noise, which is my flat signal, spectrally flat signal. And then I will look at what the spring.AR does to that. My input is A. Spring coefficient, well, let's leave it at 1. Honestly, I didn't try this before, so hopefully we'll get something. And there it is. It does something. Seems like low frequencies are high, then we have a fairly flat response there. Let's try another coefficient, spring factor, 0.1, 0.2. Okay, less low frequencies. It has some kind of funny quality to it. What happens if I blow it? Can I blow it? Who knows? Okay, I think that's kind of distorting as well. Let's take it lower, try to blow it more. Okay, so it has a fairly specific frequency there. Does that frequency change, I wonder? If I blow it further. Yeah. Okay. So it seems like we've got a kind of a high pass filter, so what they call the spring coefficient, including mass, if you increase that, you increase the frequency, and the gain is fairly high. Let's blow it further. There we go. That's your spring. I guess the guys who figured this out, put it in there, are proper engineers, and it's actually physically accurate. Obviously I have a damping as well, so let's see how that affects the frequency. That's rather damp. What does this one do? Okay, looks flat. So obviously I'm just exploring this, see what happens. Cool, and then similarly with the ball, I have a eugen called ball, which is a bouncing ball physical model. So this is the bit that tells you something about, you know, the relationship between the... No ball? I thought there was a ball. Ball 1. Ball, hello, Mr. Ball. So I was saying that this kind of shows you how closely related filters are to physical models. So simple physical models, typically they have a feedback loop because the next state depends on the previous state, and that's about that. So I'm kind of inclined to skip it at this stage. Ball, here it is, ball. Why did it not? Funny. Okay, so this is the modeling the path of the bouncing ball. So again, it's a kind of a filter. Shall we see what it does? So here we have the input and the gravity. Okay, ball, gravity. What is the? Let's try the 1. Damping. Okay, what does this do? Great. let's see, 0.1. So I'm modulating the gravity. Amazing. So I reckon that in this case the gravity is kind of too low to pull the ball back down. So if I increase the gravity, excellent. And then maybe if I do a negative gravity, would that do us a bouncing ball? Nope. We can play a bit more. Let's see. 1 gravity, damping on impact, 0.5 friction, 0.1. Didn't quite. Exciting. Let's increase the gravity then. Maybe the friction and everything is too high. Great. By the way, it might be that it's happier with the trigger rather than white noise. Let's see. No, it didn't do much with the trigger. Cool. So if you look at the help files, you can probably get closer to an actual bouncing ball. So I'll leave it at that. Great. And then the final thing to do was to code the Schroeder reverb. Great. So what was the Schroeder reverb? Well, it was 4 comb filters in parallel to start with, and then 4 all-pass filters in series, or 3. So as I said, comb filters in parallel, they are actually a multi-tap delay line. Now, just to stay true to the design, I'll just do it with comb filters. So we have an input signal, and I will use a kind of a wide impulse there. Trig 1. Oh, that's why it didn't work. I didn't do the 1 there. Shall we try it? Blew up. Great. Things do blow up. So back to this. I have a kind of a wide trigger here. What is the 0.1? Should be fine. And what I'll do is I'll keep testing this stuff. So here comes dot play. Especially if I do this. Let's create this variable as well. Cool. That's my little impulse. And then what I need to do is I need to put it through comb filters. Okay, so I have comb non-interpolating comb filter dot AR with the input value, max delay time 0.2, and actual delay time will be 0.01 dot range random to 0.2. Okay, so I'm gonna do these in series. I'm gonna do multiple random ones. That's my comb filter, and then because I want multiple of these, what I can do is I can fill an array of 4 of these, and then I'm gonna take the sum of those. Okay, so that's my 4 comb filters in parallel, and I will reuse my input variable because in series with this I will do all pass filters. Now with all pass filters, what I need to do is I need to take the output of one of them and then feed it the input. So I'm thinking, shall I do this, try to do it in a loop? Well, I could do. Let's do it in a loop. So 4 times, what I will do is the following. I will say that the input signal is all pass filter, and then sorry, all pass, I believe n, or actually let's see, what does it suggest? I think, yeah, small p, all pass non-interpolating AR, and then the input is the input, and then I can do my same thing with the random times here. Okay, so the maximum time. So the reason, by the way, why you have maximum delay times in all the UGENs that have a circular buffer, I'm adding this in because we've discussed circular buffer. So the reason is that you have to define the size of the buffer for it to stay in place, because what you're doing is you're rotating the pointer, and actually 2 pointers, typically the read and the write pointer. So they go around, and you can change the delay time by changing the distance of the read pointer to the write pointer, but you cannot really change the maximum delay time, the size of the buffer. Okay, so that's the reason behind that. So I do this, and then that's the input. So this should work to put 4 all pass filters in series, because it will run this 4 times, and each time the input signal will be called the output, which will act as the input for the next iteration. So behold, that should be some kind of filter. If I class not defined, which class is not defined? Line 5, comb n, array fill. Oh, what's going on here? Line 5, character 10. This is the line 5 and character comb n. Comb n should be fine now. Okay, array. Oh, that's a lot of R letters. That was the issue. Okay. Excellent. So that's the topology there. I mean, obviously you can experiment with this. Let's try to blow it up for the end of the class. Blow things up. Excellent. I think Schroeder never meant it to sound like this, but obviously hacking stuff is the way forward. Thanks for sticking with well, funny lecture, but I think the kind of unpreparedness and error seeking and all of those have its charm, and hopefully serve your progress. Thanks, people.